Hey everyone, imagine you could know exactly what's going on inside a locked room just by monitoring its doors and windows. I mean, that sounds like a superpower, right? Well, in the world of physics and math, it kind of is, and it's called the Guass Divergence Theorem. Today, we're going to dive into this really beautiful idea that connects what's happening inside a volume to what's going on its surface. So here's our game plan. We're going to start with a pretty simple core question. Then we'll explore two totally different ways to answer it. First by looking inside, then by measuring the flow from the outside. After that, we'll bring in the theorem itself, which is this amazing bridge between the two. We'll see why it's such a big deal, and then we'll get a feel for how it actually works. All right, so how do we get this superpower? Well, it all starts with a core question, a kind of mystery that forces us to look at the same problem from two completely different angles. Okay, let's get a picture in our heads. Imagine you've got this sealed container, and it's full of water. Now, let's say hidden inside there are these tiny, almost magical faucets and drains that can turn on and off whenever they want. The question is, without opening the box, how could you possibly know the total amount of water being added or removed at any given moment? Well, you've really only got two options. The first one, the inside method, seems logical, right? But it's also basically impossible. You'd have to shrink down, go inside the box, and meticulously measure every single source and every single drain, and then add them all up. The second option, the outside method, is totally different. You just stand outside the box and measure the total net flow of water that's actually crossing the walls. So the big question is, how on earth could these two radically different methods give you the exact same answer? Let's start by digging into that inside method. Now, to really wrap our heads around it, we need to talk about a concept called divergence. Divergence is actually pretty simple. It's just a number. A number that tells you if any specific point in space is acting like a source or a sink. You can think of it like a microscopic flow meter for our water box. At any single precise point, it tells us if that spot is behaving like a tiny faucet, a source, or a tiny drain, a sink. And this makes it really clear. If the divergence at a point is positive, you've got a source. It's like a little faucet is on, and fluid is expanding from that spot. If it's negative, you have a sink. A drain is open, and fluid is contracting. And if the divergence is zero, well, that just means water is flowing right on through that point, with no net change. Simple as that. So to get the total effect inside our box, what do? We have to add up the value of the divergence, the strength of every single one of those tiny faucets and drains, at every single point inside that whole volume. And in the language of calculus, that massive adding up job is called a volume integral. Okay, so now let's just forget everything happening inside the box for a second and switch over to the outside method. This whole approach is all about a concept called flux. Flux is a lot more direct. It's simply the total amount of stuff, in our case water, that's actually passing through the surface of our box. It's the bottom line. It's the final measurement of what actually gets out or what gets in. And this is the key difference, right? Flux couldn't care less about the chaos happening inside. It doesn't matter if there are a million tiny faucets and drains all canceling each other out. Flux only measures the final net result right at the boundary. And the mathematical tool for measuring something across a whole surface like this, well, that's called a surface integral. So we have these two completely different ideas, adding up all the tiny sources inside versus measuring the total flow right at the surface. How could they possibly be related? Well, this is where the magic happens. The theorem is this profound yet simple statement that these two methods aren't just related, they are identical. The total sum of all the sources and sinks inside the box has to equal the net flow of water out of the box. When you say it like that, it just feels intuitive, almost like a law of nature. And that's exactly what it is, a deeply powerful mathematical truth. And here it is, in all its mathematical glory. But hey, don't be intimidated by the symbols. This equation is really just telling the story we've been talking about. On the left side, you've got the surface integral for flux. That's our outside measurement. And on the right, you've got the volume integral of the divergence, our inside measurement. Guass's theorem is that big, beautiful equal sign right in the middle that connects them. This quote really gets to the heart of it. It's basically a fundamental law of conservation. It's like an accounting principle for the universe. You can't have more stuff flowing out of a region that is being created within it. Nothing just gets lost. It all has to add up. So, okay, this is a beautiful piece of math, but so what? Why does it matter? Well, It turns out this isn't just some intellectual exercise. It's a legitimate superpower in science and engineering. This theorem is an absolute cornerstone in a bunch of fields. In electromagnetism, for instance, it's the foundation of Gauss's law, which lets us connect an electric field on a surface to the electric charges, the sources, that are tucked away inside. And it's just as vital in fluid dynamics for figuring out how mass and energy are conserved in really complex systems, like jet engines or weather patterns.
And just to give you a sense of how important this isn't some obscure, dusty theorem. It's one of the big three of vector calculus, right up there with Green's and Stokes' theorems. These three ideas basically take the fundamental theorem of calculus that we all learn and stretch it into higher dimensions. They form the bedrock of how we understand fields in our 3D world.
Now, beyond all its theoretical beauty, the theorem has a massive practical advantage. It gives us a choice.
So let's say you decide to use the inside method, the volume integral. The process is pretty direct. First, you calculate one thing, the divergence of your field. Then you evaluate just one triple integral over the whole volume. It's a single, self-contained problem. Now compare that to the outside calculation. If your box has, say, 6 faces, you have to do a whole separate multi-step calculation for every single face. You've got to find its orientation, calculate the flow through it, do a tricky integral, and only at the very end can you add all 6 of those separate answers together. It's often so much more work. And that is the crucial point. The divergence theorem is a shortcut. It gives us the power to choose our own path. If you're staring down a horribly complicated surface integral, the theorem lets you just swap it for what's often a much, much simpler volume integral. And you are guaranteed to get the same answer. It's an unbelievably powerful tool for making hard problems easy. And that really leaves us with a fascinating final thought. This mathematical principle shows us that a system's boundary can hold the complete story of what's happening deep inside. It makes you wonder, doesn't it? What other complex systems, from the event horizon of a black hole to the membrane of a single living cell, can we understand completely just by carefully observing the surface?